All right, to start things off, what we're going to do is just start with kind of a recap-y type discussion of the position, velocity, and acceleration functions. You've likely messed around with these things before in Calc 1, and so likely you remember some of the kind of relationships that connect these things. We'll remind ourselves about what those are. Then we're going to define and contrast things like distance and displacement. And we'll have a small little discussion on that, and then eventually we'll end with finding the future value of a function with some initial value. This is something that you probably did in Calc 1, but we're going to look at it in a different way, and we'll use some different methodology here. Let's get this thing started then. We want to talk about the position function. I'm normally going to use S for position here. Whoops, I got to change my highlighter to be yellow instead of black. We'll talk about some position function S here. That's going to give us the position of an object moving along some line at time t relative to the origin. I want to be a little bit careful about this because we don't have to have things defined on a line, but what this means is that if our starting point or origin is this point in the middle of our circle, and if I actually did draw this circle correctly, then what that means is that this point and this point and this point all have the same position function output, because they're all the same distance away from the origin if this is actually a circle, right? So it doesn't necessarily show exactly where our object is. It just tells us essentially how far away it is from the origin if we've moved away from this kind of straight line context. So anyways, just keep that in mind. Then we've got a velocity function. Velocity is just a rate of change of position, so you've probably seen this before. Our velocity function is going to be the derivative of s, our position function. And then acceleration is just a rate of change of velocity, so it's the derivative of the velocity function, or the second derivative of the position function then. So here's a quick little example that we can play with. Say we've got some jogger that's running with this velocity function, and we want to know when their acceleration is 0, what time their acceleration is 0. So we can say, all right, the acceleration function is going to be v prime, which should be pretty easy for us to find. We'll just find our derivative, 4t minus 8, and then we can go ahead and set this equal to 0. We can say, all right, 0 equals 4t minus 8. When t equals 2. So a of 2 equals 0. Then we can answer the question, is this a maximum or minimum velocity for our runner? What we could do here is the second derivative test. The second derivative test of velocity is the first derivative of acceleration. So it's just 4. So what we'll notice is that when we plug in our t value of 2, we get something that's positive, meaning our velocity function is concave up with this horizontal tangent line. So this is a minimum velocity. We have to be careful though, because this doesn't necessarily mean that this is the time when our runner is running the slowest. If we plug this value into our velocity function and see what is the velocity here when time is equal to 2, you'll notice we get 2 times 2 squared, that's 2 times 4, so that's 8, minus 16, plus 6, and what you'll notice is that's negative 2. It's not that this is when our runner is running the slowest, because if a velocity is negative, all that means is that we have a negative rate of change of the position function, meaning that we're getting closer to that starting point, that origin. So all we're thinking is that our runner is running in the opposite direction now. They're running backwards, essentially, or they've turned around, more likely. So we just have to be careful with how we interpret some of this stuff. But other than that, this should all feel pretty familiar. Maybe, again, we have to shake off some of the rust, but no big deal. All right, so now what we want to do is we want to compare a couple of things. First, I want to show off what this displacement thing is. This is just a change in position. S of A is the position at this time right here. S of B is the position of our object at this time. So displacement is just a change in position. We already talked about how velocity is the derivative of speed. What I want to notice, though, is that this change in position, then, we can notice that since velocity is the derivative of position, that means that position is an antiderivative of velocity. And so this should look kind of like, maybe I'll write it this way, actually. This should kind of look familiar. This is the fundamental theorem of calculus, right? The position function is one of the antiderivatives of velocity, and we know that to integrate something on the interval from a to b, like this definite integral, we find one of the antiderivatives. In this case, we'll make it our position function, and we evaluate it at b, and evaluate it at a, and subtract the two things. This is the fundamental theorem of calculus. So I'll write it with this integral here. Now, what we're going to do is we're going to compare velocity and speed, and we're going to compare displacement and distance traveled. So when you look at the difference between velocity and speed, we already saw earlier that velocity could be negative, and that means that we're moving backwards, right? We have this negative rate of change of position. So if we want to just think about the scalar speed, not a vector anymore, if you've taken some physics classes, you probably understand the difference there. We're going to talk about speed. Speed is just velocity without the direction. So we throw absolute values on here, and that'll give us what we're talking about. So now if we go back to our jogger, we could say the speed at this time is actually 2 units instead of -2 for velocity. Similarly, if we just care about the distance traveled, then we're going to integrate the speed function. Let me show you the difference. Let's say that we start here. And let's say we move around and we do a whole bunch of stuff, and then we loop back and we end here as well. Our displacement is just the distance between these 2 points, right? The starting and the ending spot, which is 0. Even though we've actually traveled really quite far. We traveled this way, and then we traveled backwards. So our distance really maybe wants to account for this kind of like we went out and then we came back. We want to sum these 2 lengths up. So that's something that we just have to keep in mind. And if we don't take into account this negative velocity, this backwards moving velocity, if we just integrate the speed function, that'll work out for us pretty well. The problem is sometimes this is hard to deal with, because what is an antiderivative of this absolute value of velocity? I don't know. We're not going to have a really nice way of doing that. So the problem here is that we're going to actually have to figure out what that absolute value of velocity is. No big deal. We'll likely just split things up into a couple of different pieces and see what's going on. I'll show you how that works in a second. So let's go back to our jogger. We've got this 2t squared minus 8t plus 6 velocity function on the interval from 0 to 3. First, we're going to describe the motion of our jogger. What I think would be best is to graph this velocity function. That way we can make sure we understand what's going on here. So we'll take a look at the picture of our velocity function. To do this, I'm going to change our velocity function a little bit. I'm going to say this is a parabola. I know that's what the graph of this looks like, but first I want to factor it as best I can. That's supposed to be a 4. There we go. And then I can factor this a little bit, and I'll notice, hey, this factors into t minus 3, t minus 1. This is really helpful because now I know if that's 1, 2, and 3, I know that my parabola crosses the x-axis at 1 and 3, and I know it's opening up, so it's going to look something like this. And now if I'm cutting things off at 3, then what I'll really do is just stop right there. All right, so let's describe the motion. Remember, this green function here is the velocity. So it's not that we're starting really far forward and moving backwards and then moving forwards again. What you'll notice is that on this interval from 0 to 1, we have a positive velocity. What that means is that we're moving forward. It's decreasing, so that means we're slowing down. Then we could say on this interval from 1 to 3, we have a negative velocity. which means we're moving backwards. And we start with a small negative velocity. We get a more negative velocity, and then it comes back to small. Meaning, we go, maybe I'll just write it this way. We go slow to fast in the negative direction. So that's why we have that -2 velocity here, and then back to slow. And then we stop at t equals 3 because our velocity is 0. So we start moving forward really, really fast, and we start slowing down as we move forward. And then once we hit t equals 1, we turn around, right? We've slowed down to a stop. We turn around. We're moving in the negative direction. We speed up in the negative direction. Then we start slowing down in the negative direction until we stop. That's the motion of our jogger here. All right, so now what we want to do is find the displacement on these intervals, and we can interpret what's going on. All right, so displacement we knew was just going to be a change in position, which means we can just integrate. So on 0, 1, we're just going to be looking at the integral from 0 to 1 of 2t squared minus 8t plus 6 dt, and this should be something that's not too hard for us. Antiderivative. So this is 2t cubed over 3 minus 4t squared plus 6t. Evaluated from 0 to 1, I've got 2/3 minus 4 plus 6. What's that? 2 plus 2/3, so that's 6/3 plus 2/3. So are we looking at 8/3 here? Something like that. Then I can do on this interval from 1 to 3, I'll notice that the integration is still easy because we have the same velocity function. So my antiderivative is going to be the exact same thing. It's just going to be a little bit more annoying to evaluate things. I need to evaluate from 1 to 3. So let me evaluate at 3 first. 3 cubed over 3 is really 3 squared. So this is 2 times 9. So I'll just say this is 18. Minus 4 times 9, that's 36, plus 6 times 9, or 6 times 3, sorry, that's 18, minus this whole thing evaluated at 1, which I already know is 8/3. All right, so 18 plus 18 is 36, minus 36, that's 0, so I've got negative 8/3. All right, so then this last one should be really easy, right? Because it's the integral from 0 to 3. Of this thing. And what you'll notice is that that's really the integral from 0 to 1 plus the integral from 1 to 3. And I already have those things. So it's 8/3 minus 8/3 equals 0. Okay, so what does this mean? It means on the interval from 0 to 1, they moved 8/3 distance units away in the forward direction. On the interval from 1 to 3, they moved 8/3 units, whatever our distance units are, in the negative direction, so back. And so obviously on the whole interval, they don't actually displace, right? Our starting and ending points are at the same spot here. So that's kind of interesting. If you want to think about this visually, we were integrating things. What that means, let me grab the colors. All right, 0 to 1 was in green. What that means is that this area here was the same as this area here, but this one is negative. And so it's kind of obvious that if you add these two things together and they're the same size, but one of them's negative, we get 0. Now, it's hard to sometimes tell that by just looking at the graph, so we do actually need to integrate, but there we go. All right, so now let's go ahead and find the total distance traveled. Now, notice this is not displacement, right? We're looking at distance, so what we need to do is integrate the absolute value of the velocity function, which I'm going to draw. Let me get a straight line, although that was pretty good. I have this nice straight line tool, so I may as well use it, right? So our original function looked like this. 1, 3, and we came down through here. Our absolute value of the velocity function is going to still have this part. But then instead of going negative, it's just going to reflect this thing up above. Same image, but we're just going to reflect it above the axis because we know that the absolute value takes every negative value, in this case a negative y value, and makes it positive. So this red function is the absolute value of v of t. This is our speed function. And so if we want to find distance traveled, we're looking at the integral from 0 to 3 of the absolute value of v of t, which I'm going to notice, because I've sketched this, this is really the integral from 0 to 1 of the absolute value of v of t, which is the same thing as v of t, because it's already positive, plus the integral from 1 to 3 of the absolute value of v of t dt. But in this side of things, because our velocity function is negative, we'll tack on another negative to flip the sign. That's all we've got. And so we know what these integrals are, right? This is the integral from 0 to 1 of our velocity function. That was 8/3, plus the integral from 1 to 3 of our negative velocity function. Or if you want, you could say minus the integral from 1 to 3 here. And that's negative 8/3. So we're going to subtract a negative 8/3. And so we've got 8/3 minus negative 8/3, 16/3. So our total distance is 16/3, even though the displacement is 0. Now again, finding the absolute value of these functions is not something that we can do really easily. We have to know what our actual velocity function looks like, so we know where to cut things up and which portions to flip above the x-axis, right? This was the only region that we had to change the sign on, and it's because originally that was the negative part of our velocity function. So we have to be able to know what those portions are and know what the areas of them are, right? We found this red shaded area was negative 8/3, so that when we flip it up, we know what size it is. Okay, so we've been working with velocity and acceleration. What about the position function for our jogger? We know that the position is an antiderivative of velocity, and so we're going to integrate velocity to find it. But we're going to do things in kind of an interesting way here. So what you'll notice is that I've swapped out my variables a little bit. That's just so that I don't have the same variable in my limit of integration as I do in my function. So notice I'm integrating my function with regard to x, but t is my limit of integration. Now, since velocity is the derivative of position, the fundamental theorem of calculus is pretty easy. It says an antiderivative of the derivative of position is position. And so we'll evaluate this from t, or from 0 to t, so s of t minus s of 0. But we can solve for this really easily. So we have this integral. Oops, there we go. I keep wanting to draw t's here. Let me fix this. V of x, there we go, dx equals s of t minus s of 0. If you want to solve for s of t, we're going to just subtract s of 0 from both sides. Oops, we're going to add s of 0 to both sides. It already is subtracting. Keep your signs together. Oh man, I'm falling apart already. Anyways, so here's what we've got. We're going to integrate on this interval from 0 to t, which maybe feels weird because we maybe aren't used to having variables in our limits of integration. And then we're going to add just whatever the initial value of the position function is. So here it is written formally. Given a velocity function of an object moving along a line from its initial position at s of 0, right, when time is equal to 0, the position of the object for a future time, for the t values being greater than or equal to 0, is s of 0 plus the integral from 0 to t of v of x. Now, if our initial position is actually given to us at some time like 4, I don't know why. Maybe we had something else happening for the first 4 hours, and then we want to know a new function after time being 4. All we would do is swap in a specific time here. So you could say like t naught, right? Where t naught is just whatever your starting time is. It doesn't have to be 0. And that means this would swap out for t naught, and this would swap out for t naught. So you could say if we're starting 4 hours into this, we'd have s of 4 plus the integral from 4 to t of v of x, and that would work on the domain from t greater than or equal to 4. Most of the time, though, we're going to be having zeros here, so I'll just leave it like this. So to get our future value, we take our initial value and we add some variable displacement. Notice that this doesn't necessarily have to just be a position and velocity relationship. The reason that we could do this is, remember, velocity is the derivative of position. So as long as we keep that same relationship, we can do this for any functions. It doesn't really matter. We can take some function, and if we know the rate that it changes, then we can integrate that derivative from 0 to t, add an initial value, and we get a future value. Done. And here, you'll notice that what we used to call displacement here, right, the integral of velocity, we're just going to call net change, which is pretty much the same thing. Displacement is just the net change in position on some interval. So we'll just use a little bit more general terms if we use other functions, because it doesn't necessarily have this kind of physical, tangible thing that we recognize. Here's our example with our jogger. Let's say that we've got some sort of initial position at 2, whatever the units are, I don't really care. So if we want to know what our position function is, we can do this in a couple of different ways. What I'll do is I'll say s of t is equal to s of 0 plus the integral from 0 to t of the velocity function, but I'll write it as v of x. S of 0 is 2, and then we're going to integrate 2x squared minus 8x plus 6. Notice I'm just putting x in for my variable so I don't have this weird clash of variables. So I've got 2 plus my antiderivative, which hopefully we remember this one. We've done this a couple of times already. Evaluated from 0 to t. If I plug in t, I've got 2 plus 2t cubed over 3 minus 4t squared plus 6t, and then I plug in 0, and in this case 0 minus 0 plus 0 is just 0. All this to say our position function is 2t cubed over 3 minus 4t squared plus 6t plus this constant 2. We can use that initial value to chuck that in here. Notice that our initial value is not always this constant term, because in some functions, if you evaluate at 0, you might actually get an output. Like imagine if there were some trig functions or some exponential functions floating around in here. Evaluating at 0 may not just give you this second part of your fundamental theorem of calculus, antiderivative evaluation being 0. So just keep an eye out for that. No big deal. Notice that this feels a lot like something that we've done before. So here's another way of doing the same thing. Here's like the Calc 1 way. You've probably done this before. Well, maybe just say the velocity function, or sorry, the position function is the antiderivative of the velocity function. And so we'll say, all right, we've got our 2t squared minus 8t plus 6 dt. We know what our antiderivative is, but now we're going to be using a family of antiderivatives. So our position function is going to be in this form. We'll tack on this plus c constant of integration. And then we'll say, wait a second, we also know that s of 0 equals 2. This is our initial value. So if this is the form of our position function, let's just plug in 0 and set the whole thing equal to 2. And here we can see very easily that our constant is equal to 2. And so either way, we end up with the same position function. 2t cubed over 3 minus 4t squared plus 6t. And now instead of saying plus c, I know that specifically for this position function, with this initial value, it's actually plus 2. Cool. So another way of doing things, I think it's a helpful, useful thing, and we'll play with that a little bit more later on. But jump into some other resources that we've got, ask some questions if you have any, and hopefully that seems to go pretty well. Welcome to the class, everybody.